Great. Welcome, everybody. I'm Oliver Gonseca. I'm the CEO and co-founder, and I'm just going to do a couple bits of introduction. So thank you for joining us. We're going to share with you the results from what we call Demo Day. This was our first public kind of test of Eureka 1, which is this robot that you can see here. So both Tristan and Becky are going to talk through some of the results. But let's go to the next slide. I thought it would be useful to just summarize with what our mission is. So we are a for-profit company, but we've set the company up as a public benefit corporation, a B corporation. And so that means our directors have an obligation to not just make money for the shareholders, but also to do a public benefit. And so our public benefit, as stated on our certificate of incorporation, is to try to help mitigate the climate crisis by providing sustainable battery and critical metals. And so, our vision is really to accelerate clean energy by developing the most sustainable critical metals. And, the mission is to harvest and process critical metals from the seabed, but we are really trying to protect the environment. So you'll see we've designed all of our technology to try to minimize the harm that the extraction of these resources provide. So next slide, please. So Tristan is our software development manager. He leads the team that is developing the software that was used in the testing and that runs on the Eureka 1, and he'll go through some of the technical presentations, and Becky will then talk about some of the stakeholder engagement and what we're working with to try and get people to buy in to our approach to deep sea mining. So with that, I will hand over to Becky to talk about some housekeeping and who we have on the call. Thank you, Becky.
Yeah, of course. Okay, so just some housekeeping. If you have any questions, we have a lot. We're going to have a lot of time for Q&A at the end of this call. Wanted to keep the pardon me, I'm a little sick. Wanted to keep the content fairly minimal because we have a wide variety of people registered for the webinar today, from regulators and government through academia and NGOs, people working in this sector, deep sea scientists. So with such a wide range of people, we thought it'd be best to leave lots of time for Q&A. So if you have any questions, please go ahead and pop it in the chat. And I will be monitoring to either bring up during the presentation itself, or at the end of the presentation, we'll also have a time for that discussion. Okay. In terms of what we're going to review today, we'll have an introduction to who Impossible Metals is, the next steps for our selective harvesting approach, sort of our technology development roadmap, the Eureka 1 demo day. So what was it? And also going through some video of it and some of the detailed results and that data. Then we'll talk about stakeholder feedback, what we heard at the event. Certainly there was a lot of discussion. We're very grateful for the amount of discussion we had at the event. So it's really just sort of a summary of key points that we heard. And then how you can access the data, which is all available publicly. Everything's been made available so that everyone can review what we did at Demo Day. And we'll talk about that more later. And then, of course, Q&A. So like Oliver talked about, he talked about our vision and mission. So in order to achieve that vision and mission, we have two things going on at Impossible. One is developing selective harvesting, and one is developing a new kind of mineral processing that works through bioextraction. So selective harvesting would use a fleet meaning a whole bunch of. Oh, we have someone who wants to come in. There we go. Welcome. Selective harvesting, it would be using a fleet of autonomous underwater vehicles that would hover over the seafloor. So they're not rolling along the seafloor. There's no contact with the seafloor of the vehicle itself. It would hover over the seafloor and collect nodules one by one using robotic arms. So the robot would see the nodules and would be picking them up one by. Oh, we have more people coming on in here. And during that system of hovering over the seafloor and picking up the nodules one by one, we would be using AI, artificial intelligence, to avoid macrofauna. So those deep sea corals with the long tendrils and other things that are attached that to the nodule. So we would be looking to avoid those by using artificial intelligence. And it would allow us to program leaving nodules behind in a certain pattern or different patterns depending on the environment, with the goal of preserving habitat function. So really picking up those nodules and avoiding macrofauna and leaving nodules behind that can continue to support the environment. Certainly, there's going to be impacts with any kind of harvesting of nodules on the seafloor. It's impossible to avoid all impacts, but the goal here is to avoid loss of habitat function and loss of those macrofauna that are actually attached to the seafloor, and to allow that habitat to continue to function while gathering those metals that are really critical to supporting the low carbon economy that we want to have moving forward globally, with those metals that we need for things like batteries. So on the other end of that, you can't have sustainable or more sustainable metals just from the way you harvest or extract the metals. The way that we refine metals can also be quite impactful. So the other part of our business is working on bioextraction, which is a type of mineral processing. So what this means is that the ore is crushed, as ore typically is, to go through processing. And then rather than being put through a high energy process or a process with very harsh chemicals like arsenic, what we would be doing is putting that crushed ore into a solution with bacteria, and very specialized bacteria that respire. Their bacterial respiration, we respire oxygen and breathe out carbon dioxide. The bacterial respiration in this case would actually be putting those metals into solution. So that's the other part of our business that we're working on. Today, we'll really be focusing on the selective harvesting side. That's the side that we did our May demonstration on. But certainly, if anybody wants to chat about mineral processing and has questions for us at the end, we will do our very best to answer. We don't have our biochemists with us here today, our chemical engineers. Or biochemical engineers, as it may be, with us on the call today, but we will do our best to answer those questions, certainly, and can find answers for you if we don't have them. Okay, so that's sort of the overview of what we're doing at Impossible. Looking at more of a timeline, this would be our technology readiness timeline. So the timeline in which we think we can have this selective harvesting technology ready. Now, this doesn't take into account permitting timelines or things like that. That's a lot of other. There's a lot of other things that go into all the sorts of timelines that would actually go into harvesting a metal. But in terms of can we get this technology ready, this is the timeline we're looking at. So you'll see Eureka 1 is the little robot in the second picture. That is also what we call V3. That's the one that we did our demo day on. And we'll be seeing video from the demonstration of the capabilities of that robot. Really, where we're at with Eureka 1 is showing is this possible? How could this actually work? As we move into Eureka 2, which our team is doing now, and even looking forward into future versions, is how do we improve the efficiencies of that robot? How do we do a lot of things? So Eureka 1 was really a wonderful testing ground, and it will continue to be a testing ground to sort of figure out the core components of how we're doing these things. So we're really excited about what our team's been able to achieve with Eureka 1. So moving now into the demonstration event itself, I just wanted to provide a quick overview here about what that looked like, because everything that we presented at the event is publicly available, and we'll be providing that link to you. So just wanted to give you a sense of what we did, and therefore what might be available to you. So on May 17th, we did a facility tour, and we have a tank in our facility where we're working on IDing the nodules using our AI. The first step of training our AI to recognize nodules with life, we were doing a simple recognition of color. And so that was part of our first demo there. Of course, we'll be moving on to training the AI to recognize different forms of life. But this is sort of a first proxy that we're working on in that sense. We then moved on to the demo of the robot. So we went down to the Collingwood Harbor, and we put the robot in the water, and we did 2 missions that I'll talk about in a minute. One of them being our first completely tetherless mission. And I remember one of the attendees said, "Oh boy, you guys are either really brave or really dumb here today doing this for the first time live with us." And it turned out we were really brave, and it worked out great, and the tetherless mission went off without a hitch. After that, we talked about Eureka 2 a little bit, sort of looking forward into what that might look like. The next day was focused on presentations, about bioextraction, about a preliminary concept economic model. We had our keynote speaker from Bob Gallion, who is a battery market and critical minerals expert. And we presented the results from Eureka 1. So all the sort of graphs and charts and all that sort of stuff that goes into the behind the scenes data that we're collecting. So just to set up, Tristan, I'll move things over to Tristan in a moment here, but I'll just present this slide quickly. The demonstration, just to give you a sense of what we were demonstrating, we were not in the deep ocean. This was a shallow water test in the Collingwood, Ontario harbor. So this is on the Great Lakes in Canada. We were using decorative lava rocks as nodule analogs. Nodules are surprisingly, they have a surprisingly low density when you pick them up. I was quite surprised when I first picked one up. So the density is not that far off, and they have a similar shape variability. So they're a good analog for us, and we can throw lots of them in the water, and they're just a good analog for us. So we have these decorative lava rocks. We also put this sort of, we call it the sandbox, or a sandbox table, because the abyssal plain in the deep sea floor is quite flat. This would be a sandy surface that we have here. The deep sea has very fine sediment, but again, we're not at that stage of, that will be Eureka 2's job, is to get a better sense of the deep sea sediment. At this point, we're trying to just work through the general concept to prove the feasibility of this. So it's a sort of a sandbox that is then put down onto the floor so that we can put the nodules on it. All right, so you can see that. And then this is what it looks like under the surface. You can see the edge of that sandbox, and the nodules that are placed on it there. Okay. So this way we can sort of reseed the table over and over again. We have sort of a long tube, we put the nodules down and we can reuse it over and over and over again. And it creates sort of a great testing spot for us. This actually came out of winter testing in the Great Lakes. As you can imagine, it got very cold and the lake got very icy. So originally we had been going out on the lake to do the testing, but over the winter we needed to come up with a solution. And this was the solution with a bubbler to keep the ice from forming. And it really worked great and allowed us a wonderful testing platform. So now I'm going to hand things over to, oh, we have someone else joining. Welcome, Sam. Okay, so so now that we sort of have a setup, what was demo day? How do we set up the underwater situation for the robot to work within? I'm going to hand things over to Tristan now, who will go into what those missions looked like and how they rolled out.
Sure, thanks, Becky. Yeah, so we, on the demo day, we did 2 missions. They were very similar. The main difference, like Becky mentioned, is that the first one was a tethered mission, and the second one was the first time that we decided to go fully untethered. So both missions were fully autonomous in the sense that after we put the vehicle in the water and initialized the vehicle position so that it knew where in this nodule field it was able to then autonomously drive over to the nodule field, run a mission where it traverses up and down the table that Becky showed in the last slide, picking up nodules and bringing them all the way up through the hopper system. And then at the end of the mission, it would come back and we could recover the vehicle, bring it back on deck and see the nodules that were collected. So the first one, we, like during a lot of our development, we used the tether just for monitoring the telemetry feedback, the various sensors on the vehicle, as well as the camera feed, so that we can see what is happening. And we also, so we watched it from our user interface through the tether, and we had a separate ROV that was monitoring our vehicle. It was a small ROV that we have to give us a third-party view, like you can see in the underwater image on this slide. And then for the second mission, where it was fully untethered, we didn't have any live feedback, of course, because we didn't have a tether on the vehicle. So we just watched our vehicle execute its mission through the ROV camera. But during both missions, all the data was being recorded on board the vehicle. So after the missions were complete, we were able to review the data. And that's the next slide after this is showing the data from the untethered mission, actually. But yeah, there was a lot of leading up to this. We never removed the tether. It wasn't too brave because we had been doing a lot of testing leading up to this, where we removed the tether essentially in all aspects, except we had a physical rope essentially on the vehicle. So we'd run this mission a few times. We just decided that with the guests there, we would do the completely tetherless, no rope whatsoever on the vehicle, and let it execute the mission fully autonomously. So, but you can go to the next slide, and this here is a video. If it's easy enough for you, you might want to go full screen because some of the stuff's pretty small. But yeah, you can just maybe pause for a moment so I can just talk about what people are looking at. So at this point, this is the point, like I mentioned, all the data on the vehicle was recorded during the entire mission. And we just chopped this particular clip to show when the vehicle arrives to the table. So the mission starts on the surface, obviously, so that we can communicate with the vehicle. When it's tetherless like this, we use radio communications. There's a radio on the surface and a radio on the vehicle to tell it to execute its mission, and then it goes down and completes the mission and then comes back. And then we use radio controls for driving the vehicle when it's on the surface. So like Becky also mentioned, all of our data is publicly available. So this mission file, which includes the entire mission, if you're interested in some of the navigation of the vehicle from its home position to this table, that's all available. But the sort of core of the technology, obviously, for us is picking up the nodules. So we're doing that in this video. So yeah, this video starts. We got down there. The vision system is active right now, picking up nodules, and what we do is we map them as we go along. So Becky, you can probably hit play and I can sort of talk over things as the vehicle's moving. So yeah, that's a onboard camera on the left there that is showing us the arm feedback. And then the middle area is a 3D visualization that we create of the vehicle so that we can know, we use it for our navigation purposes as well as to afterwards review data and see what any component in the vehicle was doing. But yeah, so to talk about what the camera feed is showing is, yeah, you see nodules getting picked up by our end effector and being placed in a a tray there on the back of the vehicle, and we have a conveyor system which is running essentially an underwater conveyor, so that we're causing a thrust force that will bring the nodules up the conveyor and into our hopper, which was then they get collected and we can remove them from the hopper when we get to the surface. So each one of these nodules that the gripper is going for there, and then so what you'll see at the end of each of these lines is that the gripper gets tucked and the vehicle turns around. If you see in the bottom right there, I was changing the speed of playback of this data. The reason being is because the table, as you saw, is not infinitely long, so it's fairly short. So we had to just do one line down the table, turn the vehicle around 180 degrees, and then we would shift down like the vehicle's doing at this time right now, shifting down, and then it'll do another line. So there's 4 of these lines total in this playback file. And in the real missions, we would be doing lines that are much longer than 8 feet, which I think was the length of this test table. But yeah, so each of these nodules are getting mapped by the vision system, and then as the vehicle is perceiving itself traveling over the table, it knows that the gripper is now over that nodule, and it goes down to where the nodule was mapped, and it picks it appropriately and brings it back to that hopper location, and then it gets collected. So you'll see the slides after this will be giving us some feedback on, or some aggregate of sort of how the collection process went, but overall this is sort of the main thing that you're seeing. So this view here is our user interface, and you have access to the not just the videos of the user interface, you actually have access to the data. So you can go in and click around in all of these tabs if you want to look at any different parts of our system, the data that we recorded. There's a bunch of information right now on sort of what we're doing from a control system perspective on this main page. The vehicle controls during this time were, we had a variety of controls. So you can see the top right there, we're in altitude control mode. So we keep the vehicle at a constant distance above the lake bed, or in this case, above the table. And then we allow that the small changes in vehicle altitude relative to the table to be compensated for by the motion in the arm. We also have heading, pitch, and roll control turned on, so that the vehicle will hold the line that we want over the table as well, while stabilizing in pitch and roll. And we're holding a forward X velocity, which is the forward direction of the vehicle, traveling at 3 centimeters per second. So yeah, that's kind of the high level overview of what the control of the vehicle is doing. And then if you look at it, eventually you could go into some of these tabs if you choose to download this data and see a lot of the other stuff that our system was doing during this time. Some of the particularly interesting stuff is the vision data, which is how we actually identify nodules and map them. And what we do is we identify the centroid locations, and we have a distance to the seafloor around the nodule, so that we know that we don't dig the end effector too far deep into the sand. What we want to do is just have it get around the bottom of the nodule and pick it up without obviously causing too much of a plume. So there's a bunch of interfacing within this file that you could look at in terms of how our software is working. But at a high level, the general gist is that we are using our machine learning vision system to identify and map the nodules, and then as we use our control system to get the vehicle to move over this table, we pick up the nodules that were mapped. There's a lot of improvements that we have planned for future development. And we've been implementing those since this May demo about a month ago. We have a tow tank in our facility that we've been using that has the same arm with the same geometry and same motors. So we've been able to already start implementing some of the proposed changes that we had planned. So yeah, I think this might be the last leg now. And once this leg ends, you'll see the lights turn off. We have lights on the vehicle. I think there must be an overview in some of the, so the lights turned off on the vehicle. We illuminate the lake bed ourselves, and then the vehicle was at the end of that file. It was actually on its way to navigate back to the home position to be recovered at the end of the mission. So that's a short clip of kind of the core demonstration of what the technology of Eureka 1 is and how we pick up the nodules. So we have a couple slides now, which just do some summarizing of the success of our nodule pick. So like we mentioned, there was 2 missions. There was the tethered and tetherless mission. You guys just saw the tetherless mission, but this is the results of the tethered mission. There's a few plots here. It basically is pick attempts versus successful picks versus captured nodules. So pick attempts is just how many times the end effector went down to try to pick up a nodule. Successful picks is how many times it actually successfully picked up that nodule. And then for the captured nodules, there are a few instances where we pick up a nodule successfully, but it didn't make it into our hopper collection tray. A lot of those are because of what we're doing when we turn around at the end of those, each of those table legs. We open the gripper as we turn around. So something that we could easily get fixed, or in general is something that doesn't really affect our system too much because of the fact that we have these short legs that are not really representative of the real vehicle. And there are a couple of times though where we do miss captures of nodules if a nodule slips out on its way to the hopper tray or something like that. So sort of in summary of the tethered mission, we had an 88% pick success rate. Our average time per pick, which is something that we're always trying to improve, was 6.1 seconds. So that is actually per pick attempt. So if you want to figure out the average time per nodule received into the vehicle, you need to look at our pick success rate plus our average time per pick. And then the other stat that is mostly on something that's internally useful and representative for us is the average time from starting a pick to raising from the nodule. That's because that's a much smaller time, because that's when we start the end effector moving towards a nodule till when we start lifting the nodule off of the lake bed. And the reason that that's such a small amount of time and the total pick is just because in this particular vehicle, the location for collecting the nodule was pretty far back in the vehicle, as you might have seen in that video. So a large portion of the time was just traveling the arm from the nodule to that collection point and then back to the nodules again. So something that we're optimizing for Eureka 2. And the next slide is very similar. We just had slightly better success on the tetherless mission, although they're pretty close in most ways. But overall, the pretty similar results in both missions as we've been seeing with our testing of this vehicle. And Becky, you're muted. I think that you're taking on this slide, but you are muted there.
Thank you. I appreciate that. Thanks, Tristan. And I know that was a lot of information. Tristan is a very efficient information distributor. I took the opportunity to go around and play around in the free software that you can download to play back those missions. And I found it super interesting. So of course there's, we've put instructions together on how you can do that. And it can be really interesting to sort of play around in there. I recommend it. So we started to get some comments coming in, but we're almost at the end of the presentation. So we'll get through the presentation and then we'll move on to the Q&A and get to those questions. All right, so like I said at the beginning, the discussion during demo day was continual and in-depth. I'm so grateful that the attendees who were there were willing to share their expertise and share their thoughts. I think next time we do an event like that, I would leave a lot more space in between presentations and events, because we just had so much good discussion. So really thankful for that. One of the big issues that was brought up in a bunch of different contexts is the idea of these deep sea sediments and how they can be kind of tricky to deal with. Sometimes they can be sticky, and how that would interact with their end effectors, the claws. And, would sediment cling to the nodules, how the vision system would work within that system, because it needs to be able to see the nodules in order to detect them and then pick them up. So lots of really interesting discussion there. And as Tristan said, we're now moving into Eureka 2. And just as Eureka 1 was this opportunity to just sort of like get all this stuff on the board. Is this possible? Can we do this? Eureka 2 and beyond is where we're going to really start to get into answering these questions. And I saw some questions coming in. I saw a question about silt plumes, sediment plumes. So as we move into these next ones, we're putting a lot of work into what those claws look like, how the arms move, how the nodule would be actually pulled up into the vehicle. And that's going to be stuff that we want to discuss with our stakeholders before we ever get out into the deep ocean, and then of course be collecting tons of data while we're out there, because it'll be sort of our first time getting into those deep sea sediments, and really getting that hands-on about what that would actually be like. Another thing that came up is the idea that there's a lot of different nodule field types. So obviously we've got these decorative lava rocks on top of sand that are working really well for the purposes of Eureka 1. But as we move forward, thinking about those different nodule field types, all the way from, you know, really closely packed nodules to ones that are further apart, some that are mostly uncovered versus mostly covered. What does that look like for our equipment and what we're able to do in the deep? So really grateful for sort of the expertise in the room about what it's really like down on the deep sea floor. Continuing on, there was some recommendations to basically keep talking. Keep talking to the stakeholders, keep hearing what people have to say, just keep talking as we continue to do our design, because there's so much expertise out there. And we were just so surprised that, you know, how much expertise everyone was willing to provide. Everyone was really generous with their time and knowledge. So we will continue to have those conversations as we move forward in our design. The launch and recovery also came up a lot of times. You can imagine this being a fleet of vehicles. The idea is that a single selective harvesting robot is released from a ship. It goes down, does its harvesting, and it has the payload inside of it. So there's no sort of pipe to the surface that the nodules are coming up. So the whole vehicle comes down, it collects the nodules, and then the whole vehicle comes up. It needs to then be recovered onto the ship to take the nodules off of it. So the whole idea of that launch and recovery system and what that looks like, we had a great discussion around that. Cycle time considerations. How fast can you pick up these nodules? How fast can you get down to the seafloor and back up? And again, how fast can you unload those nodules and get the robot back in the water? So that cycle time of a single cycle is really sort of a key driver to our economics. And there was lots of great input on on some considerations that we need to think about in that cycle. The other thing would be just really seeing that at this point, Eureka 1, we're in the Great Lakes, we're using these nodule analogs, and now as we move forward, it's the time to really start thinking about those environmental impacts. What do we need to be studying during our testing of Eureka 2 and beyond? Things like sediment suspension from the arms, light, noise. What does it really look like down there? I saw that there was a bunch of comments about this, about how are you going to do this? And one of the key things that we've done is we've started to have roundtables with deep ocean scientists to say, hey, here's our idea. What do you think? And what feedback do you have for us? So the first roundtable was around just sort of the general concept of selective harvesting. We were very early in our development at that time. The second one was a more detailed look at Eureka 1 and Eureka 2 to say, here's what we're thinking. What would your feedback be in terms of what we should be looking at? What kind of studies we should be doing, things like that. So I am not a deep sea scientist, and so some of the comments I've seen, questions I've seen coming in are above my knowledge base, but that's where we're really looking to engage our stakeholders and engage the scientists that we'll be working with on those missions to collect data, and what the timing of that looks like in terms of Eureka 2 versus Eureka 3, things like that, and how that aligns with permitting processes and other needs. Like I think somebody had a comment about piggyback missions, and to have university and college students. I mean, these are all possibilities that are out there, and we're looking to talk with people about how we can make these sorts of things work. And then finally, there is an interest in bioextraction. Polymetallic or manganese nodule processing technology isn't super well developed at this point. It's a different kind of ore than most land-based mines. It's not a sulfide. So there was a lot of interest in that, lots of questions for our bioextraction rep that was doing the presentation that day. And we'll continue to keep developing that technology as we move forward. Okay, so we're at the end of the presentation. Just want to have a note here about accessing the publicly available data. I will be sending out an email to everybody with basically the same information that's on the slide here. All the data from the event is publicly available in a Google Drive folder. If there's any issues with it, just contact me. More than happy to help if there are any issues. There's an event summary document that was circulated to attendees before finalization. The data from both the demonstration missions, including instructions on how to download and use the user interface. I was able to figure it out fairly quickly, having not used it before. So I figure if I was able to do it and understand the instructions we have out there, I'm hoping that it is clear for others. But again, we're available for any questions. The presentations are available. The concept economic model is there. And then there's some videos, not only from the demonstration missions, but we put some other example videos in because we know the videos are interesting and informative for everybody. So that's what's available publicly. And again, I'll be sending out an email about that. All right, so we've come to the end of our presentation and we'll move into the question and answer portion. We've already had some questions come in, so I will be moderating that. One of the first things is that I saw a question come in about the habitat function and the macrofauna, how we will be measuring the silt plumes, percentage of nodules we would need to leave behind. And as I said, we are at the beginning stages of what the studies will look like and how we will be gathering this information in order to figure out how we would actually want to go ahead with commercial harvesting and what adaptive management would look like. And of course, before all that, how we study the impacts of what we would be proposing. So the first one was, it's amazing your process can focus on specific nodules. Thank you, Becky, another Becky in the chat. I'm really interested in something you said at the start, the leaving behind macrofauna would lead to maintenance of habitat function. The habitat function would be more about having the nodules that are left behind, at least from my discussions with the deep sea scientists. You may know better than I. In terms of being able to leave them behind in a way that they're still connected to each other for the fauna that are using the nodules as hard surface so that they can have connections between the nodules that are there rather than just having a nodule as an island, leaving areas of connection. And then I was talking to another scientist who was talking about the halo effect around a nodule. So when you're removing a nodule, it doesn't just affect the fauna that's on it and the epifauna in the sediment right at the location of that nodule, but sort of in a halo effect. So taking those sorts of things into consideration as well. Again, this isn't my area of expertise, and we'll be working with scientists as we move forward on that, and would be happy for anyone on the call who is interested to be part of that. We'll keep you in the loop. So if you're interested in being part of those deep sea scientist sort of roundtable calls to talk through these things, please let me know and I'd be happy to add you to the list.
Becky, I think we should just ask Tristan to just give a high level of how the vision system works, because
That's a great idea.
you may not understand that the selective harvesting is what's going on. So Tristan, just high level, how do we identify the nodules?
Sure, yeah. So we have our own camera system that we put on the vehicle, and it uses a stereo pair of cameras so that we get 3D information on every nodule. And we have a machine learning model that can then identify. So for the Eureka 1 demo, it was identifying the nodules relative to anything else, essentially. And from that, we are able to get the location of a bunch of metadata on the nodule, particularly the centroid location is what was most useful for us, centroid location and distance from the camera to the seafloor around the nodule. And that is how we were able to control the end effector to go to the point just right above the seafloor around the nodule and close and pick up the nodule. So essentially, every single nodule is getting individually mapped, and because we have navigation software on board the vehicle, they're getting mapped in the 3D world in terms of whether it's Cartesian or world coordinates. And then once we get the mapped location of all the nodules, we choose based on a variety of filtering. For the Eureka 1 demo, it was just radius based. We didn't want to pick up any of the nodules that were too small because they were just not as relevant to us. So we made a radius filter to allow us to pick up only nodules of a certain size. And then something that we've been working on, like Becky mentioned, was demoed as part of the May demo, is our preliminary life detection and selective harvesting technology in our tow tank in our lab. So what we have there is, again, it's the representative lava rocks, and we have most of them have been black, as you've seen in some of the images. We have some that are just naturally red. So we've been able to use the, because thus far we've been using the infrared sensing of our camera, but we're using the infrared plus the RGB camera now to be able to get color images of the nodules and differentiate between the color of the red nodules versus the black nodules and consider those ones with life and avoid picking them up. So we've been sort of developing and testing that software. And then the next level of that for us is getting whether it be simulated or real imagery with our camera, as we're working to get our cameras in the field to be able to see some of the actual nodules. But between that and simulating some of the types of macrofauna that you might see on nodules in our tank, training our model so that it also contains annotated images that say this is a nodule that contains life, and then training it to know how to avoid any of those nodules in the future. So taking a step beyond just color. So that's kind of our current and short-term future roadmap.
And Tristan, correct me if I'm wrong here, but the part of that is also there's some things that may have a small base but have like long arms. So training it to sort of go around those things and not be disturbing something that maybe has like is sort of like wide out even though there's just a small base.
Absolutely, yeah. It depends on exactly what we see and what we train it on, but the idea would be that we'd put in some sort of exclusion zone around any sort of nodule with life, ideally, so that because there's, depending on the field, there's many nodules down there, so we can just put an exclusion zone around that so that we don't put our end effector anywhere near it.
Great. So hopefully that answers some of that question. Again, like I said, we're at the beginning stages of this, and we're going to be doing more of this moving forward. Nick asks, there's going to be ability to leave behind a certain percentage of nodules. Are there any studies indicating what percentage would need to be left on the seafloor to be a sustainable level? And as far as I know, that is not a something that has a scientific consensus, and I think it may also have some nodule field dependency. Different nodule fields may be different in that sense, so that would be a key part of the studies that we're doing in sort of the environmental impact assessment for a nodule field. And then as more data becomes available from different nodule fields or from mining that would be going on, from harvesting that would be going on, you can then have that adaptive management moving forward. Have you considered the have you considered the possibility of creating a cub?
I can answer that one if you want, Becky.
Thank you. Sorry, I don't know what that word is.
So that's CubeSat, which is kind of like a standardized cube-shaped satellite for space exploration. So yeah, that's something, especially so for the Eureka 2 and beyond. The Eureka 2 is kind of in development now, so it's not something that we've really spec'd into it. But what we have done is added on a pretty wide variety of environmental sensors onto in Eureka 2 to be able to collect the possible types of data that we may need, although we still don't necessarily know all of the data that we will need to collect. So that's something that we are still working with scientists to figure out. And we've spoken about for the vehicle, which is beyond Eureka 2, sort of the V5 type vehicle, the next vehicle after that we've been talking about. And yeah, it's going to be a much bigger vehicle and so we've talked in general about the idea of having a wide variety of environmental payloads available to put on the vehicle. So I think that's something that we could certainly consider would be, because getting something down to 6 kilometers is not easy. So there's always a benefit to being able to collect data, whether it's for our benefit or for just anybody else's benefit as well. So that's something that I think is a great idea for us to keep in mind, because especially if it's something that will end up navigating itself, might be more challenging. But if it's some sort of sensor package, I think that's something that feels like it'd be something we can certainly keep in mind for the next generation of our vehicles. And Becky, if you want, I can take Robert's next question, because it's a good one. Yeah, how you be observing and measuring silt plumes generated by your process to keep in line with proposed limits by international bodies. We are aiming to limit plume creation, but like Robert asks, how will we show that we are within limits? So that's something that we are in progress in terms of the technology development, and again, receiving feedback on the best ways to do that. So for the next generation of vehicle, we have, like I said, some environmental sensors, including turbidity sensors, to try to be able to read our localized plume. We have, like you saw, that monitoring camera that was the main view you were seeing in that video. We have many monitoring cameras on our next vehicle to be able to monitor video of the plume, and we have the lights in place to be able to illuminate all of the plume appropriately. And we're investigating the idea of things like a multi-beam sonar to be able to use acoustics to measure the plume as well, and figuring out sort of the best ways that we can measure our localized plume, and then have missions designed where the vehicle will then drive back into the plume that it's created and give a better representation of what was actually generated. So some of those higher level pieces are still in development of how we feel we'll best be able to do that. And one of the things, which I don't know we really mentioned in too much detail here, is in our in-house we have a 1 degree of freedom tank, which is essentially just an arm and an end effector that goes down into an aquarium filled with sand and water and picks up nodules. And it's what we've been doing our development, rapid prototyping on, to figure out what types of grippers are most effective and which types produce the least amount of plume. And in there, we have vision processing software that does automatic plume detection. So that's been something that has been great for us for the development of our end effectors, to determine which ones create more or less plume. And then we're trying to figure out the best way to incorporate that onto the actual vehicle itself, and between localized and more general plume generation, how we can best capture that is still sort of something that we are developing.
And end effector is a technical term for claw, if you're not familiar with it.
Yes, I should have.
At the end of the arm.
That one took me a while to figure out, I'll be honest. Okay, Becky said roundtable discussions would be great with EIA specialists too. Yes, absolutely. I come from the EIA world, but not from the deep sea EIA world. So I'm very, very interested to speak with environmental impact assessment specialists and get a better sense of what we would be looking at moving forward. So great recommendation, and something that I think would be super interesting and really valuable for us. I think another question for you here, Tristan, from Raul. Are you planning on harvesting against the direction of the bottom current to mitigate the impairment of the AUV sensing systems by stirred up sediments?
Yes, absolutely. That's a very astute point. And yes, that's part of our sort of harvest plan, more of your traditional, mine plan for mining, but for us, we have to design sort of the surveys of the vehicle of how it traverses the seafloor. And one of the main things is, we would be heading into the current, and we've received, we've been collecting data, not ourselves, but receiving other people's data on the currents at those depths so that we can spec our vehicles to have thrusters that will still allow us to move forward at the desired speed for our collection while heading into the current to allow this to mitigate the impairment of some of the sediment that we do pick up. So that is exactly what we plan on doing.
Yeah, it's also worth mentioning that the cameras are looking ahead of the vehicle. So any local disturbance that we create, we can mitigate by having the vehicle move at a constant speed. And so that way we can predict where the actual nodule is or where the life is, even if it was obscured by sediment at the time we came to pick.
Yeah, that's a good point. Yeah, I didn't really cover that before, and it's not so obvious with the one. Well, there is multi-cameras in a Eureka one, but it's essentially a one-camera, one-arm system. But the next vehicle has more arms and more cameras, and so on and so forth. And it's essentially a wall of cameras or a line of cameras at the front edge of the vehicle. So we map all of the nodules, and then as the vehicle traverses, we are using our micro navigation to determine where the nodule is relative to the vehicle, and then the vehicle can, the end effector can pick it up. So during some of our testing, we definitely were not super efficient at limiting our plume, but we were still able to pick up nodules because, like we said, we mapped the nodules ahead of time. So the sediment actually doesn't enter the vision camera itself. The monitoring cameras may be disturbed by it, but the actual mapping cameras in the front of the vehicle won't really be affected by the sediment that we create ourselves.
And that's something that we will be testing to make sure is true in those finer or very fine sediments of the deep sea. So that brings us to an end of the questions that I've seen in the chat. Thank you very much, everyone, for your questions. They're all very insightful and helpful. Is there anything else? Please pop it in the chat if we have any other questions. But maybe Oliver, did you want to say any sort of closing remarks here as we close things out for the day?
Yeah, I can do. I want to thank everybody for their time and the great questions. We really want to be transparent. We do think we're somewhat reinventing the way deep sea mining can happen by using a vehicle that doesn't land, it hovers, it uses selective harvesting to only pick up the nodules where we cannot see visible life. And then we use the vehicle itself to move up and down the water column. So we don't have a riser pump system with all of the noise pollution that it would give out, or a tailings discharge plume, which is something that the other systems have. So, we've really spent our effort to architect a solution that minimizes the environmental impact, and also in the economic model comes in at significantly lower cost as well. So that's really the mission that we're on.
Great, thanks, Oliver. And we'll be hoping that you all continue to follow along in our journey and provide your thoughts and questions. Very appreciated. And like I said, there'll be a follow-up email after this webinar to make sure that you know where to access the data that's available online. And if you have any questions about, or you're having any issues, please let me know. I'm happy to assist. Or if you have any questions that come up after this that you think of later, please, get in touch with us and we're happy to answer. So I think we'll wrap it up there today. Thank you all again for attending, and look forward to seeing you in the future at potentially another webinar that we hold, letting you know when we have another update to let you know about. Thank you very much, everyone, for attending. We really appreciate it.
Thank you.
Thanks, everyone.
Bye.